In this video, we're going to take a look at power supplies and transformers, in particular in power supplies. Here's the block diagram of a power supply. The input is usually a line input with 120 volt AC. Then there is a transformer that is used to electrically isolate the rest of the circuitry from the power supply, from the line power, and also usually to transform the voltage down to some smaller level, for example 10 volts or 12 volts. Then at this point we still have an AC voltage, and that needs to be rectified and made into a DC voltage. So this would look something like that. The AC voltage looks approximately like this. And then once we get to the point here, the rectifier will cut off, for example, all the negative parts of this sinusoid, something like this. And then you use a capacitor, like this one here, in order to compute the average of that voltage. You would have something like a V average, which is the DC voltage that comes out here. And then in the end, some regulator has to be here, which is making that voltage constant. At that point here, the voltage can vary depending on load. So here we have varies, depends on load. And by this we mean the load that's being connected to the output of the power supply. And also it depends on the line voltage. So that is the voltage that comes here from the outlet with the 120 volts. That can vary by as much as plus minus 10%. A transformer consists essentially of two coils or inductors with inductances L1 and L2 that are placed close to each other. In a typical transformer, one of the windings is wound first and then the other one is wound on top of it. Magnetic flux produced by the first inductor, this is usually called the primary side of the transformer. So the magnetic flux that's produced here, shown in those blue lines, that links to the second inductor L2 and induces a voltage at the terminals of L2. So what we have here, what goes between L1 and L2, that is the magnetic flux that links L1 and L2. And so if you have a sinusoidal voltage or current at the input, then we're going to see a sinusoidal voltage at the output, and how large that voltage is will depend on the number of turns, N1 and N2, that we have for the primary and the secondary side. So here is the secondary side. And the turns ratio is defined as the number of turns on the secondary side divided by the number of turns in the primary side. So if we go from 120 volts down to, say, 12 volts or something like that, then this turns ratio is going to be a number that's less than 1. In fact, it would be 1/10 if we go from 120 volts to 12 volts. The voltage at the output of the transformer, which is V2 of t, is related to the current, in fact the derivative of the current at the input, times N1 and N2, those are the number of turns of the primary and the secondary side, and this quantity M, which is called mutual inductance. Each of the coils of the transformer L1 and L2, has an inductance of its own that's determined by the number of turns and the magnetic medium on which the coils are wound. And then there is the relationship between the two. If those two coils are far apart from each other, then the mutual inductance is small. If they are close to each other, then that mutual inductance is large. And there is a limit as to how large that mutual inductance can be, which is determined by L1 and L2. And here's the formula for that. The mutual inductance has to be actually less or equal to the square root of L1 times L2. And this less or equal to is expressed here in terms of that constant K. That constant K is called the coupling coefficient. Okay, the coupling coefficient has to be between 0 and 1, as shown here. And a good transformer will have a K that's very close to 1. In fact, typical values for large transformers in power distribution come close to something like 0.98 or 0.99. And an ideal transformer would have a coupling coefficient of 1. In order to analyze transformers in a reasonably simple way, we assume that we're looking at an ideal transformer. And as I just mentioned, an ideal transformer has a coupling coefficient of 1. So that's one requirement for an ideal transformer. The other requirement is that there is no loss of power. Okay, so the transformer is a device that receives energy or power from one side and passes everything on to the other side. It doesn't heat up or use any of that power for itself. Okay, and for an ideal transformer with a coupling coefficient of 1, it can be shown that the output voltage V2 of t has to be equal to little n times V1 of t. Little n is the turns ratio, as we discussed before. It's the number of turns of the secondary coil divided by the number of turns of the primary coil. And in the schematic, this is usually shown in the form as a 1 colon n, and that just means that we have this ratio n of turns compared to 1 turn on the primary side. So the n is on the secondary side, the 1 is on the primary side. Then the no power loss, that means that the way it is labeled here, we have passive sign convention from both sides. So V1 of t times I1 of t is the power that comes in from the left side. V2 of t times I2 of t is the power that comes in from the right side. And if there is no loss, then the sum of those powers has to be equal to 0. Okay, so that is shown here. Now, if this equation here is true, then that means that V2 of t times I2 of t has to be equal to minus V1 of t times I1 of t. And if we solve for I2 of t, we find that this is minus V1 of t over V2 of t times I1 of t. And this V1 of t over V2 of t, that's 1 over n, 1 over the turns ratio. And so we get this result here, that the current at the output of the transformer is minus 1 over n times the current at the input. Notice that the minus sign comes from the fact that both currents here are pointing in, so that we have passive sign convention on both sides. Practically speaking, on the left side, the current is indeed flowing in, and power is delivered to the transformer. And then on the right-hand side, we connect some load, and the current actually flows out to the load, so that the secondary side acts as a generator, or is generating power from the point of view of the load that's connected on the outside. So that's the significance of the minus sign here. in terms of the relationship between V2 of t and V1 of t and I2 of t and I1 of t, what we can state is that as the voltage goes down on either side of the transformer, the current goes up and vice versa. So here's a little example. A transformer with the primary side 115 volts AC and the secondary side 9 volt AC, and we assume that it can deliver 1 amp on the secondary side. So the turns ratio is the 9 volts divided by 115 volts. It's 0.078, so it's less than 1 because we go from a high voltage to a low voltage. And for the current, I2 of t we say is 1 amp, so that's equal to minus 1 over n times I1 of t. So that implies that I1 of t is minus n times I2 of t. So that's here minus 0.078, which is the turns ratio, times 1 amp, which is the current that it can deliver. And so we get minus 0.078 amps AC. Again, the minus sign here comes from the fact that we used passive sign convention for both sides of the transformer. So the transformer uses 115 volts AC and 78 milliamps AC on the primary side to deliver 9 volts and AC and 1 amp AC on the secondary side. And the reason why transformers are being used, besides this ability to transform voltages from one level to another and thereby transforming currents from one level to another, is that the primary and the secondary side are electrically isolated. Okay, so if you touch the secondary side of a transformer, you are not touching whatever potential the line voltage has that comes from an outlet. And the energy is transferred through a magnetic field between the two sides, and so that provides that isolation between primary and secondary side.